Energy is involved in every physical and chemical process. In this video, we will predict how heat and work are involved in physical and chemical reactions. Here are some equations we used in first semester general chemistry. Earlier in Chem 1B, we looked at how fast or slow reactions occur. We'll look at thermodynamics, which tells us, does a reaction occur? A reaction energy diagram gives us a lot of information about reactions, so stop the video and answer these questions. So here are the answers. Activation energy tells us whether a reaction is fast or slow, so since the activation energy is small, this reaction is fast. By looking at the relative energies of the reactants and products, we can determine whether the reaction is exothermic or endothermic. Since the products are lower in energy than the reactants, this reaction is exothermic. So thermodynamics tells us about the initial state and final state, which are the reactants and products. Kinetics tells us about what happens in between. When a cold object comes in contact with a hot object, heat is transferred due to that difference in temperature. When a chemical reaction occurs, the amount of heat transferred is equal to the change in enthalpy for that reaction. Delta H is calculated from Hess's law. If no chemical reaction occurs, we can use this equation to calculate the amount of heat transferred. Note that mass, specific heat, and temperature determine the amount of heat transferred. Pouring hot water into cold water is an example of a physical heat transfer. We could use this formula to figure out the amount of heat transferred and to calculate how much the temperature changes. So stop the video and review this calculation. So note that if we pour a small amount of cold water into a lot of hot water, the temperature doesn't change very much of the hot water. When a fuel burns, such as food, energy is released, that is, the reaction is exothermic. We can take advantage of the heat lost by that exothermic reaction to heat up something. Now, a chemical reaction occurs when reactants collide with sufficient energy for bonds to break or form. So stop the video and answer these two questions. Here are the answers. It's like breaking a stick. To break a stick, we have to supply energy. If we could somehow reform the bonds in the stick, energy would be released. When hydrogen reacts with oxygen in the combustion reaction, water is produced. Energy has to be supplied to break the HH and OO bonds in the reactants. Energy is released when the HO bonds in water are formed. Note that there's more energy released than supplied, so that makes this reaction exothermic. Hess's law is used to calculate the change in enthalpy, or delta H, for a reaction, which tells us whether a reaction is exothermic or endothermic. Remember, there are tables of standard enthalpies of formations that we can look up these values to calculate delta H of the reaction. Stop the video and review this calculation of Hess's law. A formation is a reaction in which a substance is produced from the elements in its standard state. Elements in their standard state, such as hydrogen and oxygen, are high in energy, unstable, and reactive. When elements form compounds, such as water, note that the water is lower in energy, which means it's stable and unreactive. This difference in energy tells us delta H for the reaction. Chemical reactions are frequently used to heat up something. For example, you use your gas stove at home to cook food. Let's do this example. How much water can we heat up from 25 degrees to 100 degrees by burning 1 gram of hydrogen? When hydrogen burns, that's a chemical heat transfer in which Q equals delta H. The heat lost by the chemical reaction equals the heat gained by the water. The heat gained by the water is a physical heat transfer. We'll use this equation to figure out how much heat is gained by the water. So stop the video and review this calculation to calculate the mass of water that can be heated up. So hopefully you calculate that X equals 390 grams. That is the mass of water that can be heated from 25 to 100 degrees by burning 1 gram of hydrogen. A fuel produces heat when it's burned. In a car engine, we want a fuel to also produce work. Here's a schematic of a heat engine and an engine cylinder and piston. So stop the video and answer these questions. Here are the answers. The hot reservoir is the engine cylinder and piston where the combustion reaction occurs. That combustion reaction produces heat. Some of that heat is converted to work. In a car cylinder, carbon dioxide and water are produced in the combustion reaction for a carbon-based fuel. The exothermic reaction will cause an increase in temperature, which will cause the gases to expand. More moles of gas products than gas reactants will also cause the gas to expand. Work is the ability to move matter. Turns out that not all of the heat is converted to work. Not all of the gas molecules in the cylinder are pushing against the piston to produce work. The efficiency of an engine is the output divided by the input, which is the work divided by the heat from the hot reservoir. Note that the heat which is not converted to work is lost or wasted. Work is the ability to move matter. In physics, work is defined as the force exerted through a distance. If we do this to that equation, and know that pressure is force divided by area, volume is distance times area, we'll get this equation which we'll use in chemistry. In chemistry, work involves gases. Remember that liquids and solids are incompressible. When a gas expands, the final volume is greater than the initial volume. That means delta V is greater than 0, which means work is going to be less than 0. When work is less than 0, that means work is produced, that is, work is done by the gas on something else. For example, the exothermic combustion reaction causes the gas to expand and do work on the car piston. On the other hand, to contract the gas, we have to supply or do work on the gas. For example, a compressor in a refrigerator supplies work to compress the refrigerant gas. Comparing heat engines, a diesel engine produces more work than a gasoline engine and is more efficient. Here's how we can determine how much work is involved in a chemical reaction. So stop the video and read these 4 steps. So when methane burns, it doesn't produce work. Stop the video again and repeat those steps for gasoline. So when gasoline burns, work is produced. More moles of gas products than reactants will cause the gas to expand and produce work. Let's see how heat and work are involved in a refrigerator. Stop the video and show heat in, heat out, and work in the heat engine schematic. A refrigerator is a heat engine in reverse, so work is supplied to remove heat from the cold reservoir. Some of the work is converted to heat, which goes into the hot reservoir. How is air cooled inside the refrigerator? So let's take a look at the phase changes that occur with the refrigerant as it goes through the refrigerator cycle. So here's the refrigerator cycle. In step A, a compressor compresses the refrigerant gas from a low pressure gas to a high pressure gas. We have to supply work to compress a gas, so work is going to be greater than 0. Heat is neither gained nor lost to or from the surroundings, so heat equals 0. Stop the video and determine Q and W for steps B, C, and D. So here are the answers. Condensation is exothermic, so Q is less than 0. Note that we have 1 mole of gas going to 0 moles of gas, so delta N is negative, delta V is negative. That makes work positive. In step C, a high pressure liquid goes to a low pressure liquid. We can assume that no heat or work is involved. In step D, the liquid evaporates to a gas. So that process is endothermic. Note that we're going from 0 moles of gas reactants to 1 mole of gas products. So delta N is positive, delta V is positive, so work is going to be negative. The step that cools air inside the refrigerator is going to be step D. When the refrigerant evaporates, it's got to gain heat. Where does the heat come from? Well, it comes from the air inside the refrigerator, which loses heat. To lower the temperature of the refrigerator below room temperature, we want the refrigerator to have a low boiling point. Modern refrigerators run on isobutane, which has a boiling point of minus 12 degrees Celsius. Since part of the refrigerant cycle involves the refrigerant being a gas, we want the refrigerant to be compressible. Note that a refrigerator costs about $20 per month in energy to run. As scientists, we want to be able to control how energy can be converted from one form to another, so stop the video and identify the equation which tells us the first law of thermodynamics. And the answer is this one. This equation tells us that the energy inside atoms and molecules, which is called internal energy, can be converted into either heat or work or both. So let's practice. Stop the video and describe the conversion of one type of energy into another for these three processes. And here are the answers. In a hydroelectric dam, the potential energy of the water above the dam is converted to kinetic energy as the water spills over the spillway. That's converted to mechanical energy as it runs the turbine, which is converted to electrical energy. For a battery, chemical energy is converted to electrical energy. That involves an oxidation-reduction reaction. And in a car engine, the chemical energy of the chemical reaction is converted to heat, which is converted to work, which then drives the car with mechanical energy. Electricity comes from the conversion of one type of energy to another. In 2009, most of our electricity came from burning coal. In 2019, most of our electricity came from burning natural gas. Much of our natural gas comes from hydraulic fracturing or fracking. In 2019, we got about 2% of our electricity from solar and about 7% from wind. Note that more solar energy strikes Earth in an hour than all the energy we consume in a year. If we can figure out a way to inexpensively convert sunlight to electricity, we could solve our energy problems.